Okay, welcome to Computer Science 3015, Functional Programming at the University of Wyoming, Fall 2020 edition semester. I'm Professor James Caldwell, but I go by Jim, and we're going to start off by reviewing some basic concepts of discrete mathematics that you learned in discrete mathematics 2030 that, just to give you a reminder. The point is that if we're going to be doing functional programming, we need to know what is a function, and we need to know a few other things about functions. So mathematicians think of functions as sets of pairs like this. This plus zero is defining a set of pairs, and it's going to turn out that that set of pairs has the conditions required to be a function. So there's additional conditions which we're going to talk about below, but in a minute. But this is the basic idea of a function. So these happen to be functions for adding 0, adding 1, and adding 2 to a set A, which is the finite set 0, 1, 2. And then it turns out that the output of this is B is also the set 0, 1, 2. So for example, if I add 2, 0 plus 2 is equal to 2 mod 3. 1 plus 2 is equal to 0 mod 3. And 2 plus 2 is equal to 1 mod 3. So that's an example of a function. Now, for sets A and B, we have the Cartesian product, which is named after René Descartes, who thought of this idea of putting things together in groups and pairs, and he used it to make geometry, which was not algebraic, into an algebraic form. And we're finding it useful for almost everything, for grouping things together. So the Cartesian product, A cross B, is the set, and we're defining this set by set comprehension. It's a set of pairs, and I'm writing pairs here with the angle brackets, whereas at Haskell it's just the parentheses. So it's a set of pairs xy such that x comes from the set A and y comes from the set B. Now, you may think that this, don't be fooled by these examples that this must be finite. Functions are mostly infinite. So consider, for example, a function that takes a number, let's say a natural number, and so that's the input, and the output is going to be a Boolean value. And so that means our pairs are going to look something like K comma B. And what I want this to do is I want it to say whether or not K is an even number. And so K is an even number if there exists a J, which is a natural number, such that 2 times J is equal to K. And so if I take this thing and I put it in parentheses and I say B is equal to that, meaning B is equal to the truth or falsity, maybe I can write it like this to get rid of the idea that, to make it more logical, if and only if B. So B is going to be true if this particular formula here is true, and B is going to be false otherwise. And so this would give me back the function. So what this set of pairs going to look like? It's going to look like something like 0, true, 1, false, 2, true, ... goes on forever. So there's an example of a function that takes an input, which is a natural number, and gives an output, which is a Boolean. Now, there are lots of functions that take more than one input. So you might think of, like, for example, let's see. Well, here's an interesting example. Is that, like, if you want to think about given two rational numbers, like let's say P and Q are rational numbers, and suppose epsilon is also a rational number, and we want to say P and Q are equal if they're within epsilon of one another. And so we want this idea that P and Q So this has a lot of inputs. We want this to turn out that this is the input, and the output is going to be a Boolean value, true or false. And so we've got P and Q, and if all we had was pairs, we've got our epsilon, and then we've got our output value B. And so this is going to be what the function. Now, we could assume that we have arbitrary couples, and so then we could say something like, okay, so the input is P, Q, epsilon, and the output is B. And now, what do we want to say? Oh, we want to say that P minus Q is less than epsilon if and only if B. So that means if this P minus Q is less than epsilon, that's true, so that means B must be true. And if B is true, it must be that P minus Q is less than epsilon. So, if you want to think about this, it's kind of, if you don't care about, let's say, more than one decimal place of precision, then, under this relation, let's call this equivalence mod epsilon, or modulo epsilon, and so then we could say, okay, P, we could write this as P equals Q with the epsilon under it. So, for example, 1/2 is equal to mod 1/10 55/100. And so you can figure that out, and you'll see that if you subtract 55/100 from, I guess I need to put maybe an absolute value sign there, 55/100 from 1/2, you get back something that's less than 1/10. I think it's 1/20. All right. that's a function that is, again, a predicate. It's mapping. The input is P, Q, and epsilon, and the output is B. So in this case, we write that equivalence epsilon. And in Haskell, we would write : has the type Q, arrow, Q, arrow, Q. I guess I should say this differently because it actually doesn't have that type. It has the type that is Q, 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 arrow, bool. And, and if I'm trying to write this as a Haskell type, then this is actually fractional. Arrow, bool. So the arrow is the thing that indicates that you're in the function. This is the function type. This is my domain A, and this is my codomain B. Okay, so let's go back to the main line of discussion and look at so here's an example of Cartesian product. If you forgot that, you can look at this. The notes are in a PDF file with the same name as the link to this lecture. So now here's something that, I'm not sure if they go over this carefully in 2030 or not, but a relation R is a subset, so remember that subset of some Cartesian product. So remember, the empty set is a relation because the empty set's a subset of every set. The full Cartesian product is a relation, but it turns out that we have certain constraints on functions that the full Cartesian product, A cross B, is not a function in general. If B has only one element, then I guess every relation is then it is true that A cross this single element set is a function. But otherwise, in general, if B has more elements than one, then you can't have the Cartesian product turns out to not be a function. And that's because we have this constraint. The constraint is that the relation has to be functional. So a relation R is functional if each element of the domain A occurs at most once as the first element of some pair in R. Well, that's a loose definition. We're going to give you a more mathematical one in a minute. And but look, each one of the things that we defined before up in the example 1, plus 0, plus 1, plus 3, all those functions mod 3, they are functional. If you look back up here at plus 0, that, 0 occurs and that it only occurs once, and 1 occurs once, and 2 occurs once. But if we take, so those are functional, but if we take the union of any 2 of these, we're not functional, because if you take, for example, this union this, you're going to have a set that contains all those elements, and 0 is going to be paired with 0, but it's also paired with 1, and that's not functional. So what we're trying to rule out here is, what's not allowed is that you can't have some set A and some set B, and you can't have any point X that goes off to 2 different points. Now, this is perfectly okay in a relation. Like if the relation is parent of, then, you're going to have a father and you're going to have a mother. So you're going to have 2 elements in that relation, but it is not functional. It doesn't determine uniquely. You don't have just one parent. So the relation is parent of is not a function, but the relation is mother of is a function. Here's the formal definition of a function. If I have 2 sets, A and B, so I've got A and I've got B, and F is a subset of A cross B. Now I'm using F here suggestively that what we're doing is we're defining a function. So F is a function if it is functional. And here's the property. It has to be that every X in A and every Y and Z in B, X is paired with Y in F, and X is paired in Z in F, if that those 2 things imply that Y must be equal to Z. So over here, we're saying, look, if X goes to Y and X goes to Z, then Y must be equal to Z. They must have been the same thing. If this is a function. Now, we can try to make more sense of this definition by looking at doing some simplifications or modifications. So one thing is that if F is functional, we can write F of X equals Y instead of X comma Y is in F. So now let's rewrite 1 up here as this formula for every X in A, for every Y in Z and B. F of X, if F of X equals Y and F of X equals Z, then Y must be equal to Z. So here's the picture again. These things must be equal. Now, until you have practice at this formula can seem, okay, look, it's got universal quantifiers in it. Like, what does that mean? That means for all. And you may remember that this symbol, this is element of, and this is an and or conjunction. And this is implies. So the formula maybe looks a little complicated, and then try to understand it can be tricky. So one thing you can do is you can rewrite the formula using logic, and we can rewrite it, logical equivalences, and we can rewrite it this way, which I have found teaching this material before, that students sometimes find this more suitable. It says, look, for every X and Y, and for every Y and Z in B, for every X in A, and for every Y and Z in B, if Y and Z are not equal, So we're looking up here. If y and z are not the same point, then f of x, so I'm mapping across here with f of x is not equal to y, or f of x is not equal to z. So you might say, well, okay, but what happens if, like, f of x is, it could be that we're looking at a situation like this. Let's say we have an x prime, and x prime writes to w, let's say. And so this is saying, look, if w is not equal to y, let's say w is not equal to y, that implies f of x prime is not equal to w, or f of x prime is not equal to y. Okay, that's true. What if we pick, instead we pick y and z like we have here? So we pick y is not equal to z. So this seems a little bit weird because x prime doesn't even go there. And so here I say f of x prime is not equal to y, or f of x prime is not equal to z. So it's just the formula that's above. But look, that's true because the w that f of x prime is equal to, f of x prime is equal to w. So f of x prime is not equal to y. That's true. Or f of x prime is not equal to z. That's true. And the truth table for or says, oh yeah, true or true is true. So even if I pick points over here that aren't related to the actual output, this is saying for every point over here. And so x prime is going to become one of them. And then you kind of iterate through all possible pairing of points over here in the set B. And you say, okay, is this true for all of those? So anyway, I mean, if that may help you understand this kind of condition, this logical condition, but in a way, what it boils down to is that any element from A can appear as the first element of at most one pair in F. Okay, so a kind of a final point here is that what if, is that functions are called total if everything in the domain maps to something in the codomain. There is a y. So, this is basically saying, look, you've got some set A, you've got some set B, I've got, let's say X, Y, Z, who cares? I don't need to label them. And let's say in B, I've got a bunch of things. Everything over here in every X in A has to go somewhere. So it basically means you can't have, okay, this goes there, let's say, and this goes there, and this goes there. You can't have a point like this left over in A that doesn't go somewhere. And if that's true, then the function is total. Now, so every point over here gets mapped somewhere. You don't have this situation. This can go over there like that. Now we've got f is a total function. Now, it's also the case, though, that there's language that's used that says, if f is not total, we sometimes call non-total functions partial. And this actually is kind of important for computer science and functional programming, is because, suppose I have some function that takes these inputs and it maps them somewhere. And suppose it does just fine, but on this input, so I've got some function f here that I'm computing, but on this input, f loops forever. So I'm trying to draw this kind of diagram, picturing what this function looks like. What do? I mean, it never gives you an output. So it never specifies anything in B. So this is partial. F is partial if this is true. Now, we'd like to guarantee that all the functions that we write are total. I mean, the other reason that that it could be that the function is partial is that suppose that on this input it doesn't just loop forever, or crashes. What if it crashes? Then f always just stops. It doesn't give me anything in B. So that's another case where f is partial. And so it turns out that this is going to have some really interesting implications in the type system, because it's going to turn out that we can write a little program that loops forever in Haskell, and that's perfectly okay. And then you can ask Haskell, what's the type of this thing? And it's going to say, this thing, it has every type. And that's weird, but we'll talk about that later. Okay, so thanks so much for listening, and talk to you soon.